In this video, we are going to show how you can model counterfort returning walls using Staad software. We check space and then we launch the program. Then we finish. We create the first node. We know that the width of the counterfort, the length of the base is 4.5 meters in the z direction, and the center to center dimension of the toe is 0.8 meters. Alright, and the spacing of the counterforts in the S direction is 2.5 meters. So let us do more. This is 2.5. So we've been able to get this. The height of the returning wall is 7 meters. So we can copy and paste in the positive y direction. So we've been able to get this done. Okay, the next thing we are going to do now is to model the counterforts first for ease in so we launch this. This direction, let's okay, even though the division will likely look too big, but let's just let it be that way. We are modeling the counterfort returning wall for a total length of 10 meters. A total length of 10 meters. Alright, after this we can take care of the base. Let's allow it to be 10 also, so that it will match with the counterforts. Okay, in another development we can model the toe. Let's give this 3 divisions. Let's give these three divisions. Okay, we can now model the stem walls. Though even though the divisions of the counterforts are looking too big, but we can reduce it. We can reduce it. Let's take this. Obviously, for this we have to maintain this same division of 10 so that the walls can intersect with the nodes of the counterforts. Right, you can actually model a single returning wall and then do translational repeats, which I think will be better, but I didn't think in that direction before commencing. But either way, you will still arrive at the same result, but at a faster time. Okay, so we've been able to get the structural system. So we can go over to general. The thickness of the stone walls is 0.3, and that will be the thickness of the counterforts too, but the thickness of the base is 0.5. Alright, so we can assign the properties, and this for thickness of 0.5, and we can take this. So we can assign so yes, and another view we can assign these two. So if we try to take a look at the 3D of what we've done, we should be able to see something like this, which I think is consistent with what we are looking for. So we are going to assign supports. We say foundation. We want to check for cell structure interaction. The modulus of elasticity is the modulus of subgrade duration is 50,000. You can set the spring to compression only, but we are going to leave it for some reasons. By the time we do our combinations, there shouldn't be any issue. If you set it as compression, it means the springs cannot take any tension, and we are going to have a little challenge when we are applying the horizontal loads. But by the time you do the combination of dead load, the vertical actions and the horizontal actions, there shouldn't be any issue. So since we are not going to consider the horizontal actions alone, let's neglect it and move on. We are going to okay, so we can change the view, and we can select the plates in this direction, and make sure that we've selected only the plates that we are interested in. And then we can assign the supports. The soil has been represented as springs. This is just like a flexible approach to the analysis. So we have to define our loads, load case details. We treat this as the self weight of the soil. In another load case, since we'll be using the same factor of safety, let's allow surcharge and let's say earth pressure. Let's separate them. um Let this be the surcharge load. Okay, we really don't have water pressure, groundwater pressure on the wall, so we'll let that be. We define the self weight. First of all, we need to be sure of the unit weight of concrete so that we can set it as appropriate. It needs to be 25, and let the pressing ratio of the concrete be 0.2. We can close. Okay, we go back to our load case details. For self weight, we'll add. Now for earth pressure, we know let's assign this first of all to the selected plates. Now we know that the earth pressure has a value of about 44.82. Okay, so we add earth pressure. So we have to treat it as a hydrostatic load. So we have to select the members. So if we change the view, we've been able to select the members that will experience the earth pressure action. It's in the global y direction. Now the load is gonna come. Let's take it to the global z direction, and now this is minus 44.289, and that's what we have. Say add, and if we check what we have, you can see that the action has been applied on the walls of the stem. um, so in the same time we can apply the earth pressure load on the base. um, we are going to apply it all over. um, Plate load is gonna be the full pressure on the plate with a value of 133 in the negative y direction. And if we change our view, we want this load to be applied at the heel alone. um, if we take a look, so we can assign to selected plates. Alright, we can go to the surcharge action. We can go to plate load. This is gonna be in the global Z direction, and then we have a surcharge action of 3.33 on the walls. Say add, and then we have in the global Y direction a surcharge action of -10. So based on the direction, this is supposed to be negative Z. Alright, so this also we are going to place it right at the base. And this we are going to apply it on the walls. So we already have a good idea of where we are going. So the next consideration we need to make is for the combinations. Let's combine all the actions because they can add together. Even though in a more detailed analysis there are other considerations you need to take. Let me call this serviceability limit state, where I multiply everything by the factor of 1. Even though there are sometimes you make different considerations depending on the action that is beneficial and the one that is unfavorable. But let's not go through that for now. And let me call this the ultimate limit state. Let the self weight of the structure be 1.35. Let this be 1.5. Let surcharge and earth pressure be 1.5. We'll just leave it that way. There is nothing else left to do. We go to analysis and print. We say all. um, and then we can go to post print, add the actions, the analysis results, and then we can analyze. Okay, we've been able to carry out the analysis successfully. um, you can already see the deflected profile of the returning wall, but we're not interested in that. This is a 3D. This is under such harsh pressure, so we dive straight to ultimate limit states. You can see the deflected shape and the movement of the wall and the structure. We dive straight to the plate actions. You can now view the bending moments in the S direction due to the applied load. We can turn off the label for the supports so that we can see clearly what's going on. Okay, you can see the plate action, the maximum moment here in the range of 109. The maximum actions also having a span moment of say 3.08. Can also get the bending moment values at the points of intersection of the counterforts. We can view the bending moments in the y direction. This will give you better the bending moment on the walls, close to 23.8 at ultimate limit states, 89 point something at the intersection of the walls and the plates. You can view the shear, the high values of the shear force. You can also view the axial forces that are developed in the counterforts. Looks interesting. So that's how we can, by the time you arrive at this point, you can now see how you can pick the factors and you pick the analysis results and proceed with your design. Thank you for watching, and please remember to share our video.